So my name is Brian, and my talk is 10 billion a day, 100 milliseconds per, monitoring real-time bidding at AdRoll. So some of you know me. I am Troutwine in Erlang and Erlang channels. I do things to and with computers. In particular, I am very interested in reliable, complex, and critical systems. So these are systems that must always work, are very difficult to make work, and if they do not work, something disastrous happens. These are difficult systems to make, which makes them fun to make. Right now I work for a company called AdRoll. So AdRoll is an advertising company, but it's less this being a style of advertising where you buy large blocks of what we would call impressions, eyeballs on an ad. So in the old days, you used to go to, say, the New York Times, and you used to say, I have $50 million. How much is $50 million going to buy me worth of advertising space in your paper? Which is fine if you've got $50 million or even $50,000. But there are a large group of people, companies, that don't have such large advertising budgets. They have $10,000, $100. So online advertising has moved increasingly to cater to these smaller advertisers. And as a result, advertising has become more this. This is data-oriented advertising. Advertising exchanges, what we call exchanges, started to appear in about 2009. It became impossible to buy individual impressions. So instead of going to the New York Times and saying, I need $50 million worth of advertising, you go to Google and you say, I need $10 worth of advertising in the next 10 minutes, which makes advertising, if you're, say, a small Etsy seller and you make octopus bracelets out of forks, much more approachable. So you need much less budget, and many more people are able to do it. And instead of managing these large relationships with companies and with large sales teams, we use real-time system engineers, which is me, and mathematicians, which is not me. AdRoll is an ad tech company, so that's what this style of advertising is. It's just technology that we happen to apply to advertising. This type of advertising is called retargeting, and it's all about data. So AdRoll uses what we call first-party data. We collect from the pixels that we have scattered around the web information about people that browse, and we correlate them inside of our system. So our customers are the people that want to show ads to people who might care to see them. So as an example, I subscribe to The Economist. The Economist has advertising that is really expensive. It's like $100,000 per month for a full-page spread. They advertise $40,000 watches. Even though I buy The Economist, I will never buy a $40,000 watch. That is totally wasted. So we partner with these exchanges. These are people like Google, Twitter, Facebook that run these ad slot auctions. So an ad slot is where in your web browser an ad appears. When you start loading a web page, there actually isn't an ad that's scheduled to appear there. What happens is there's an auction that's held. This auction takes 100 milliseconds. So while your web page loads, real-time systems all over the globe are bidding furiously to show you their ad. That's real-time bidding. So this is what sophisticated shops like AdRoll do. It means that we take all the data that we have. Our mathematicians build models. They predict whether or not an individual person will care to see a certain ad from one of our customers. And in honest-to-God real time, we bid while the user's web page loads. So the nature of the problem domain is it's low latency. We have less than 100 milliseconds. 100 milliseconds is actually our deadline to get the request from the exchange over the internet, do all of our computation, and then send it back to them. And that entire chain, including the 2 hops over the internet, has to take less than 100 milliseconds. It's a firm real-time system. So for those of you that aren't familiar, a soft real-time system, real-time systems, you're always hustling on a clock. You've got some deadline. Soft real-time system, the computation that you're performing, if you go past the deadline, your computation still has value. You don't care too much, but you try and hit the deadline. A hard real-time system is one in which when you go past the deadline, your computation has no value and something disastrous has happened. So think about an avionics system. If the pilot jerks the airplane this way, it should go that way. A firm real-time system is one in which when you pass the deadline, your computation has no value, but nothing disastrous happens, at least not immediately. So that's what we do at AdRoll. Our bids have no value past the 100 millisecond point, but nothing disastrous happens if we miss 1 or 5% of them. We're highly concurrent. So the title of the talk is actually wrong. When I submitted it, we had less transactions per day than we do now. And this slide is actually wrong. We peaked over 42 billion recently, I think, and we're growing all the time, which is really fun. And we never shut off. So we're 24/7 and we're global. So if you think about quantitative finance, they run 10, 12 hours a day. We run constantly. So the problem with building these types of systems is that we are very good at producing complex systems that we have no understanding of. So Carlos Bueno wrote this fantastic optimization book for Facebook where he said that humans are bad at predicting the performance of complex systems. Our ability to create large and complex systems fools us into believing that we're also entitled to understand them. You can substitute performance for maintainability. You can substitute performance for anything that you would actually care about for a real-time system. And when we try and overcome this, we have multiple methods for doing them that are all insufficient. For instance, ahead-of-time verification is not sufficient. That's testing, documentation, type checking. These are all valuable, so we can't scrimp on them, but they only demonstrate the limits of our system under certain artificial conditions, anything that we're able to think up. Ignorance and complex interactions with the external systems are why we can't have nice things. These are why ahead-of-time verification only addresses part of the problem. So our ignorance reduces our imagination for test cases. We can only test what we dream to test up. And the interaction with external systems introduces uncertainty into the boundaries of our system. So this becomes even more pernicious as your system grows in size or ambition. So in our experience at AdRoll and in previous experience in similarly large deployments, at scale, even rare events happen frequently. So in testing, if you have an event that's going to happen every 1/1,000,000th of the time, it's going to come up in production, and it's going to come up a lot. But you might not catch it in testing. And that's a real problem. At scale, bad things happen faster than humans can respond. So the worst thing about these rare events is that they just start pouring in, and there's no way to handle them without some form of automation. The results are often not very pretty either. These rare events are things that you have not thought of. I have no systematic theory for why this is the case, but we humans seem particularly good at imagining the not-so-bad things that can happen in our systems, but we are very bad at predicting the disastrous things that can happen. More to the point, these causes are very rarely quick to discover, which is a problem when you have tens of thousands of these pouring in and something terrible is going on. So for those of you that are not familiar with American history, the photos behind these slides, which I think you can make out, are from the American Dust Bowl. The Dust Bowl is an excellent example of individual action in aggregate causing a disaster. You had farmers who individually would strip their land of native grasses and plant wheat. They would leave basically dirt most of the year, and Oklahoma and the middle of the United States is very windy. There aren't actually trees there naturally. So you have an individual farmer do that. Maybe the farmer's kitchen gets a little messy from dirt blowing in, but when you have tens of thousands of farmers over hundreds of thousands of acres leaving just raw earth, combined with wind, you have dust storms that black out Chicago several times a year. You have President Roosevelt getting dirt in his cups of tea. Massive, massive problem. So what can we do to overcome our ignorance and our lack of imagination and avoid systems faults? How can we make reliable rather than perfect software? So perfect software is this ideal on the mountain that I contend we will never reach, simply because the world in which we live is more complicated than we can imagine. So I advocate that we have to observe our systems while they run. We have to be scientific about this. So we monitor our systems, and we provide sufficient instrumentation to apply the scientific method to our creations. So we can create hypotheses about cause and effects, and we can experiment and watch data that comes in and out. It's just science at that point. It ends up being an artifact of the universe. Problem is, not all systems are monitorable, just as not all are testable. So correctly instrumenting, effectively instrumenting a project is a matter of design and is a matter of culture. So a design that's monitorable is one that takes stock of its internal tolerances and its external interfaces and exposes these to an operator. So an operator is a distinction that I'm making based on a fantastic book called Digital Apollo, which I can't really get into, but I have a bibliography at the end of these slides if you would like to read all the books that I reference. So an engineer is responsible for building and designing systems. The engineer is the person that dreams them up and the person that executes on them, and the operator is responsible for running them. So ahead of time verification, testing, type checking, these give the engineer intuition about the system, and this is vital. Intuition about the system before it runs allows the engineer to assert things about tolerances. It allows the engineer to assert things about how the running system should look. Because if we don't know how the system should behave, you can't say how it shouldn't or isn't. Monitoring gives the operator information about the running system. So the operator, being responsible for running the system, actually develops more affinity with the system over time because they have more experience with it. And this gives them a different insight to the system, which is valuable, extremely valuable. Thankfully, the operator and the engineers are often the very same people. So this holds not just in software. One thing I'm very fascinated with in the sort of critical engineering culture is the US space program, which you can probably tell eventually from these slides. Mission control is staffed with astronauts that aren't flying at the moment. So you have this concept of, I know the system very well and I am operating it, or I know the system very well and I am in the middle of it. You see this in nuclear engineering and other settings as well. But it's a very powerful thing to operate the system that you have also created, because there's a potential for a positive feedback loop of quality here. So when we can combine practical experience, intuition, with the deep knowledge about systems, we can do really amazing things. So case in point, the X-15 was an early NASA experiment. This is NASA spelled with a C, which was a thing. The X-15 was basically a plane that would go to the edge of the atmosphere and then was intended to come back down. It was one of the first computer-controlled, computer-flown airplanes. It was thought, perhaps, that the airplane could be completely automated, but it was found that when the computer completely controlled the plane, it just skipped off the atmosphere like a stone. It was also found that when you disable the computer, the human operator, the pilot, was not able to re-enter the atmosphere either. Ended up just skipping off the atmosphere like a stone. So a combination of the two, a man-machine interface was necessary. And that's basically what instrumentation builds. That's a much deeper talk, and I would be very happy to talk about that later. So what in particular are we doing in AdRoll? One of the main libraries we use is a library called XOMeter. So historically, actually, we didn't use XOMeter. Historically, we pumped all of our metrics coming out of our systems through our sophisticated machine learning HBase cluster. Problem with that is you get delayed times. You have to wait for your metrics to batch up, and it takes 30, 45 minutes for them to compute out, which is disastrous in a situation where your system is exhibiting behavior that you didn't expect or that you declare to be a problem. So XOMeter is it's a metrics collection, aggregation, and reporting library. And it's got excellent pedigree and a fantastic focus for the scale at which AdRoll is working. So it's been created by Fourier Labs. It's open source. It has an extremely responsive upstream. On multiple occasions, I have reported an issue, and it's been fixed within an hour or so. I have no idea actually how this has been done, because I know I've been reporting this at upstream's midnight, and it still is fixed. So the metrics aggregation, the collection, and the reporting, these are all decoupled. So when I say that I'm collecting a metric, I don't also have to declare where it goes. I can simply collect it and decide at a later date where to send it, or at runtime decide to send it to a new system, even if I've already declared where to send it. It has static and dynamic configuration. So dynamic configuration is what you would expect. The static configuration, everything is brought online when the application comes up, which was remarkably useful. And it has a very low and very predictable overhead. at runtime, which is valuable for me where I am extremely latency sensitive and I'm extremely concurrency sensitive. So I'm able to predict the behavior of this tool that I'm introducing into very hot, short code paths. So some terms about XOMeter. So a metric is just a measurement. It is just a value at time of a thing. An entry is a receiver and an aggregator of metrics. So an entry is something like a histogram, a spiral, a counter. A reporter is an entity which samples the entries on a regular interval and optionally ships these to some third system. There are several reporters already baked into XOMeter: collectd, statsd, local file, and they're also very easy to add. We added the statsd integration ourselves, and it took me about 35 minutes. A subscription is a definition of the regular interval on which the reporter samples entries. So the metrics are not reported as they occur, they are polled, but they are polled in an extremely efficient way. So you have a chance to aggregate over some time interval and then ship it off the network. So this is static configuration of entries. Of particular interest are function definitions. This has been one of the most marvelously useful aspects of XOMeter, and I don't know that it's been replicated anywhere else in any other open source system. So a function entry allows me to define a function as a point of measurement. I invoke the function. So in particular here, I'm invoking Erlang memory, which is a built-in function, and I'm feeding it two arguments, ETS and binary. So what I'm doing is I'm going to record the value of my ETS consumption, and I'm going to record the value of my binary memory consumption. And then I'll eventually report that. There's also a match syntax. So because functions don't, of course, have uniform return types, you need to have multiple ways of dissecting function returns. So match allows us to, so this is for Erlang statistics, and I'm looking at garbage collection, because I'm very curious about the garbage collection in my systems. If I'm creating too much garbage, that's a problem. Garbage collection, or Erlang statistics, excuse me, if you don't know it, returns a tuple. It's sort of peculiar in that regard. Match allows you to just match values out of a tuple. This was recently added. This was an example of me saying I have a need, and then a couple of hours later finding a present under my tree. So a spiral. So one thing I forgot to point out, the predefines there, the functions, those are all VM supplied, but you can also, of course, supply your own aggregation points. So these, the Buddha is the name of the real-time bidding system. It's also the name of a delightful dog that is often in our office. Frequency cap is a thing that's internal to the system that I won't get into, but these are application specific. The spiral here is an aggregation type that allows you to collect values for some fixed time. So by default, a spiral is 60 seconds long. If you insert something at time 0, it reflects in the aggregate metric, and then at time 61, that value has been dropped out. So it no longer reflects in the aggregate statistic. So reporters. Reporters, if you remember, are things that report values over the network. This is report statsd. We use a product from a company called Datadog. They are a fantastic dashboarding company. They have a daemon that runs on your local box, and it exposes a statsd interface. So this is why we use statsd. And you can see that I'm configuring it for localhost and things like that. Here I am telling the reporter to poll for the entry named Erlang GC tote call, and I am telling it to report this over the network as a histogram. So when this is pulled out of the VM, it's of course just pulled out as a singular value. I'm telling statsd, which does some of aggregation on its own, to compute a histogram of the values. Statsd aggregation, if you can avoid it, is probably a good thing because you don't have any configuration of it. I actually don't know what the time width of this is, which is a problem, but it's not been so much of a problem that I've moved the source of truth all into XOMeter. But you can see that I actually am pretty finicky about some things. So if you don't know statsd, gauge is a statsd type, and it is the sole type in statsd that assumes that the client is going to compute the aggregate value. So if you need your application to be the source of truth of aggregate statistics, you have to use a gauge. Just as an aside, if you ever design a protocol, please look at statsd and then don't do that. you cannot, for instance, insert a Unix time value. So the value at which a metric occurred is simply the value at which it was received. So you always, eventually, you come to the realization that you cannot use statsd except but locally, which is madness. Subscriptions. So a subscription is the polling interval. So you see here again that we're telling statsd to poll Erlang statistics and run queue in this particular case. The subscriptions occur in milliseconds, which is pretty typical. So every 1 second, I'm getting the run queue backup of my system, which has been really useful, and we'll actually talk about that in a second. And again, so when you configure one of these subscriptions, you give it the metric name. XOMeter is very interested in metric names. That is the primary way that you end up configuring XOMeter and discussing metrics. Each of the aggregate statistics has multiple attributes. You'll see histograms in a second. One happens to be one of the aggregate statistics of Spiral. Of course, you can do this all dynamically. You see here that I am creating a new histogram metric called a histogram, and get value is a function in XOMeter that allows you to see all of the aggregate values for some metric. So this is actually how, instead of digging through the documentation, which is very large and complex, it's also extremely well documented, Mike, it's easier just to see at runtime what's available. And then I configure a reporter. This is report TTY. Report TTY just prints it out to std out. Please never ship a production system that has this enabled, but it's so useful at development time. And you can see that once I enable it, it just starts printing out. Because I've never put any values into a histogram, it's always 0. So in particular, at AdRoll, what are we looking for? How are we using XOMeter? So we're looking for VM killers. And all of you should have some idea of what the VM killers are, atom tables that get too big, reaching your ETS limits, things like that. We have those instrumented, and we have alerts for those. Actually, we have alerts for those if we even get remotely close to them, because that's probably a bug in the system, and we have to address that. So we're looking for system performance regressions. So that's, we use Amazon EC2. If our CPUs become slower for some reason, we want to know this. But we also want to know if our network ability has dropped. And we want to know for some key metrics in the application. So bid request latency is very important for us. Like I said, we're very latency sensitive. So we monitor how long it takes us to respond. And if we find that we've got a spike in response times, even if it's not causing timeouts, we need to know that, because we either need latency to stay the same or decrease over time. So we're looking for abnormal system behavior as well. We'll get to this point in a second. And we're also looking for surprises. So surprises are just things that are clearly wrong and clearly mean there has been a bug introduced into the system, either through system updates or shoddy deployments. So what in particular do I mean by abnormal system behavior? This is actually one of the most important topics and one of the most difficult things to discuss. It actually requires the combination of the intuition of the engineers and the operators. It is sort of the core consideration of testing and monitoring, and it's hard to decide what your system should be doing and shouldn't be doing. So for the real-time bidding system at AdRoll, no spend, where we don't bid and we don't spend any money, is an abnormal behavior. We always want to be spending money. Too high spend. Our campaigns have budgets. Our campaigns are associated with our customers. You know, if they're making octopus bracelets out of forks and they have a $100 budget and we go ahead and buy $10,000 worth of advertising for them, we're eating that overhead. Discontinuous drops in spend. So if we see that we're spending at a certain level and then blam, we're not dropping, or we jump way up with no explanation, that's also something we need to understand. And node failures, et cetera, things like that. So case studies. How has this impacted us at AdRoll? So for the first one, the timeout spike. So by timeout, I mean we've gone over our 100 millisecond limit. There is an acceptable background of timeout spikes simply because the internet is unreliable. Exchanges usually give us some fixed percentage of timeouts that can be allowed to occur. If we go over that fixed percentage, then they do what's called throttling. They cut our traffic. And that is a serious problem because the amount of traffic that we are able to pull in from the exchanges directly relates to our ability to survive as a company. Critical systems. So this is a graph of our bid timeouts. Our bid timeouts. It's a period from 6 a.m. to 9 a.m. For some exchange. I can't actually tell you which one. So what we should see is this being nice and flat, some Brownian motion around basically 0. But what we see here instead is periodic peaks of timeouts. Now, we never went over the throttling limit. This is about 2% of our total traffic, in the worst case at about 8 a.m., which peaks at 5.8K. But it was enough of a concern that it was always just below being inserted in our sprints. And then once we had increased our instrumentation, it became sort of first project to demonstrate the efficacy of this. So we examined our system load. The boxes have pretty continuous load, so we're not seeing that the boxes are overwhelmed at any point, periodically. So when you do this sort of debugging, of course, you have to make hypotheses. Maybe we're running out of CPU. No, we are not. But we can correlate that we have network traffic spikes with these same timeouts. I happen to know that we are not getting anywhere near our box's network I/O limits. So it's not that, but we do have something interesting. There is something else going on to cause this spike on the system. And this was new. So we had only just recently started charting our run queues. And you'll notice that these run queue spikes are pretty correlated with the spikes in timeouts. That was a big deal. So what happened here? So we have our scheduler threads locked to the CPUs of our boxes. And we have a background process that kicks on every 20 minutes. And it does things to logs that we produce. But it gzips them. So it consumes quite a bit of CPU time. Unfortunately, we didn't have a CPU shield enabled in our boxes. So we have n number of CPUs, and we have n scheduler threads in the VM, and they're all bound to those CPUs. And we have gzip come on, and the operating system kicks them off. So we have one scheduler thread that gets bumped off of its CPU. It backs up, and because it backs up, it's not able to process its request anymore. So the process requests timeout, and then we get that spike. The gzip turns off. Everyone settles back onto their processor cores, and then we keep on humming. So we eventually enable the CPU shield. We have dedicated processors simply for the VM. Solving this actually required quite a bit of knowledge about the system as it was deployed and about behavior of the system. Another example, so exchange throttling. So this is kind of one of our disaster scenarios, right? So this is healthy bid request. It's diurnal, right? People are not browsing the web as much at midnight. So each one of these troughs here is people sleeping in a geographic location. Each one of the peaks, it actually peaks around 11 a.m., so people browse the web a lot more while they're at work, I guess. So this is good. Like this is a good day for us. This is a bad day for us. This is actually a space of about 3 bad days for us. So we found for this particular exchange that without any alarms on their part, without any notification on their part, they just tanked our traffic. They stopped sending us as many bid requests. So every time a web page loads, 5 ads come up, we get 5 bid requests, unless we're in a throttled scenario. So we can be throttled because of various things. Primarily, we time out. But we didn't see any timeout peaks here. So this is the first differential of the bid request rate. On the right-hand side, you can see the previous diurnal chart, and on the left-hand side, you can see the throttle trough of doom. It is very useful to be able to apply aggregate statistics to these types of things because the human visual cortex will convince you of things that don't exist or that you want to exist. So you have to dissect your data. And unfortunately, we confirmed that we did, in fact, have a problem. And we confirm that with the external system, with the exchange. So especially when you're dealing with coupling with an external system, you have to request information from the external system because maybe they have a problem or maybe you have a problem that you're unaware of. So we looked at all the other metrics. our run queue, our CPU, our network I/O, they were all fine. And we hadn't deployed, so all of our boxes were unchanged. They were humming along fine, and then blam, they're crashed out. So we also asked Amazon, and we asserted that there was no network problem. So from every point of view, our stuff was good. So what happened here? We hit an implicit limit with the exchange. Arguably, it's a bug. So we have this external system inside of AdRoll called the cookie match system. So an exchange keeps an ID for every individual user. And AdRoll keeps an ID for every individual user. And we ship these IDs over to the exchange. And we say, when a bid comes, if there's a correlation, send us a bid. We had shipped 1.6 billion cookie matches over to the exchange. Unfortunately, their limit, which was not advertised, I will point out, was 1.5 billion. So this triggered an edge case in their system where we went over their implicit limit, and so they thought that we had a bug and decided to throttle us so that we weren't spewing silly ads. We didn't have a bug. We just have a lot of customers. Unfortunately, they didn't send us any emails. We didn't have alerting well enough to detect this and just report it to them. We do now. So lessons learned from all of this. So it is possible to have too little information available to you. That's the case with the implicit throttling. We did not know what had occurred until we reached out over a long holiday weekend and heard back eventually after too many days. So you see this historically as well. So during the Chernobyl accident, the firefighters were sent up to the roof, and they were kicking radioactive burning graphite back into the reactor. They had no idea this was a very dangerous thing to do. There was no good education of the population. Even while the reactor was burning, a radioactive volcano, people were going out and they were buying bread, carrying it out in the open, and then coming home and consuming it. So it's possible to have too little information during an accident. It's also possible to collect too much information or present it badly. So you see this at 3 Mile Island. 3 Mile Island had a control room that was basically this stage and then doubled. And all along the walls you have these lights, and you have 8 to 10 people that stand in the control room and they monitor a certain section of the wall. And to correlate, what they do is they yell across the room. So during normal operation, Bob, valve number 10, 10%, check. But during an accident, everyone's excited, everyone's afraid because they don't know what's going on, and they don't want a nuclear volcano, right? So they're getting loud, they're yelling, and they're missing things, they're missing information. But because you can't have one person with an overview of an extremely complex system like a nuclear reactor, they missed what happened, and it caused a meltdown. In particular, they had a valve stuck open. And it was easy to mistake that the valve was stuck open for reasons that it shouldn't have been stuck open for reasons that it should have been stuck open. Indirect knowledge may not tell you the whole story, or worse, it may make you doubt what's plainly before your eyes. So that's the first differential thing, right? You have to confirm in multiple ways that what you think is happening is actually happening. So we see this actually in the Apollo 13 disaster. The Apollo 13 popped an oxygen tank and blew off half of the ship. Mission control for the first 12 minutes of the accident debated very hotly whether or not the Apollo service module had been struck by a meteor. They were so certain in the design of their system that they could not believe that a fault had occurred in it. And they wanted to rescue the mission. They wanted to land on the moon. They eventually didn't, of course, because while they were dithering over whether or not a meteor had struck the ship, they lost oxygen in oxygen tank 1, which popped, and oxygen tank 2, which is an interesting example of, if you're going to make a redundant backup system, for God's sakes, actually make it redundant. They were connected by the same series of pipes. And they were considered to be redundant enough. So some things with instrumentation monitoring don't work quite like you would hope. So problems. Instrumenting increases code size. It takes time and it takes effort to insert this stuff into your code, and that's code that you have to maintain. While very low, the runtime impact is not zero. In certain critical paths in the AdRoll code base, we can detect when we monitor because we see it elsewhere in the system. It backs us up a little bit. So we sample some of our instrumentation. We run it every 1/10,000th of the time, which if you remember back to at scale, things happen very quickly. We end up getting multiples of those a second. So the instrumentation of dependencies, if you pull in libraries, which we do pretty extensively, those aren't instrumented. And you're going to have different ideas from the library implementer about what is valuable to instrument. So possible solutions to this. Dtrace system tap hookups. So these are facilities provided by Solaris, OS X, and Linux that allow you to have the kernel examine a running program. The Erlang VM is instrumented with these. In a month or so, I'm actually going to start digging into this more deeply. If anyone here is doing this currently in production, please talk to me. I would love to talk to you. Another possible solution is a culture of instrumentation by default. So just as we built a culture of testing by default, we also have to have the knowledge that these things are going to be running for years, especially for Erlang deployments, and we have to be able to get information about how they are running. And then if neither of these will address your problem, the Erlang virtual machine has tracing BIFs, which I'm sure a great many of you have used. They do have, unfortunately, runtime impact, but they are remarkably useful. We trace in some in some code paths, we do trace live. Insanely useful. Another possible solution, Wombat. It was mentioned briefly this morning. If you want to know more, ask an Erlang solutions person. I've seen a demo of it. It's very impressive. Duncan McGregor right there has also seen a demo of it. He was also very impressed. It won't solve everything, but it goes a long way toward. So implementation by default is not easy, and it's not free. Possible strategies for that. Application configuration. So you have your application take a module that it will simply call into periodically. Behavior callbacks. So Cowboy, for instance, when you implement a request handler, has functions that you can optionally implement to instrument the flow of a request. We do this at AdRoll, and it is remarkably useful. And the value at time functions. So these are the built-in Erlang BIFs, which you saw that we have hooked up into XOMeter. The Erlang virtual machine is studded with information about itself. It is one of the most reflective environments that I've ever deployed anything in. I strongly suggest you take a look if you aren't doing it already. So I've talked a lot about design, but what about culture? So it's possible for an organization, so a complex organization of humans, we have irrational behaviors. We're actually pretty vicious creatures sometimes. It's possible to misuse this data that's coming out of our systems. So if a fault occurs and somebody happens to be the poor schmuck sitting at the computer when the fault occurs, it is common to blame the operator and then scapegoat them and just say, well, it was his fault. But I contend that if your system has a fault that a human can cause, it is still a fault with the system. You have to design for humans just passing out and mashing their head on the keyboard. So don't look for scapegoats, look for solutions. Don't be fooled by overconfidence in your work. So we've worked very hard to build very complex things, and it is possible to feel that it is infallible. But I guarantee you it is not, because you have not been able to think through all of the possible machinations of the universe in which we live. Similarly, document and discuss all of your failures. Every time a failure occurs, it is an opportunity to learn why it occurred and then how to avoid it in the future. If you do not do this, you will continue to fall into the same traps. Everyone has to work to the same end in the team. So, for example, if I am interested in taking the real-time bidders and making them extremely highly concurrent, but I ignore latency, right? I can potentially increase latency to the point where we actually crash the company. So everyone has to have the same idea in the real-time bidding team of targeting this nice middle ground between latency and concurrency, and we also have to decide what is a nice middle ground. So everyone on the team, if you're going to be instrumenting, has to have the same end in mind, because you have to instrument with that end in mind. Similarly, know some basic mathematics. So statistics. When someone asks what's the 99th percentile of a certain metric, you have to know what that is. You have to know some basic calculus so you can discuss rates of change in complex systems. It gives you a relatively unambiguous language for discussing concepts, which is remarkably useful, especially in stressful system accident times. So this gets harped on a lot, undergraduate computer science all the way up, but it bears repeating. Prefer to be loosely coupled when possible, and be very explicit about your tight coupling. You can't always avoid being tightly coupled to an external system, but you have to know that you are tightly coupled. A lot of system accidents occur because of implicit tight coupling. You don't know that there's some system that you depend on has developed a fault, so when a fault occurs and you can measure that it's occurred, you don't know how to diagnose it because you're not aware of what's happened. Loose coupling gives you some breathing room in that situation. You still continue to work. As an example, the real-time bidders do not actually display any ads. They only bid on the ads, and then there's a notification path to what we call the ad servers. The ad servers actually display the ads. They are loosely coupled. If the ad servers go offline, the real-time bidders continue to bid, even though we're not displaying the ads, and vice versa. If the real-time bidders go offline, every ad that we've guaranteed we're going to show, we continue to do it. It's somewhat of a problem that we can continue to bid but not show ads, but our ad servers have never gone offline, so we're not super concerned about it. Measure much, but present only that which you're certain to need. So this is the same problem with there's too much information available to make to understand it. But when you are digging into a problem, if you have not measured something, you cannot make a hypothesis based on it. You can, but measure, don't guess. If you are ever in a conversation where you say, I bet the system did, stop yourself. Just go measure it. You can measure it. This is really the empirical problem. If you have not got data about something and you are trying to make a decision based on data that you're just dreaming up, you are going to make a mistake. You are going to make a decision based on data that does not reflect the nature of reality. Similarly to that, be accurate in what you measure. You are making decisions on this data. If the data is not reflective of the reality in which you are operating, you will not make good decisions. And not making good decisions is really the problem of building these complex critical systems. We can't make perfect software, but if you are able to provide enough information to people so that they can make reasoned decisions about the software, you can make reliable software. And reliable is really the best we're going to be able to do, unfortunately. It would be nice to make perfect software. Questions? Yes.
Do you throttle that, or do you throttle? I mean, at what point, it just seemed like you could instrument everything. I mean, I'd get excited now and instrument everything.
Yeah, yeah.
And then it would pour in and my system would just collapse under the weight of stuff coming in or back up. Or...
Yeah, so the question is, you have a massive data coming into the system. How do you handle that onslaught, and how do you make sense of it?
And how do I throttle, like, okay, I don't need it right now. How do I feed that back to the actual...
Gotcha. And how do you... So aggregating ahead of time is not pre-measure optimization. So instead of recording every metric and pushing it out over the network, aggregate in, say, a histogram or something like that. If you have data that you do need perfect representation of, consider that very carefully.
Okay. All right.
So you aggregate ahead of time, and then, so with Datadog, we build dashboards that have sort of overviews, and you can dig in to more complex metrics. But you have to, at that point, have the understanding of the engineer to know what's valuable to look at. And sometimes, of course, you're wrong because you have an imperfect knowledge of the thing that you've made.
Okay. And is there feedback to the front of the system that's actually doing the work, and you throttle that down so there's less?
So that's the fun part. You can actually then feed all of this back into the system and make the system decide what to do about itself.
So that actually happens.
Yeah, you can do that, and it's fantastic. You can give the knowledge, give the system self-knowledge. Yeah, tell the autoscale group we need more boxes, we need less boxes, throttle the number of requests that we're bidding on, things like that. It's
I think you're
good
right
stuff.
About the culture. I think changing the culture is definitely going to be part of it.
Yeah.
Thinking more about this. Okay, thank you.
Yeah.
That's great.
If all the data being pushed into Datadog, do you monitor each individual box via a web port or something as well, or is it strictly through the dashboard?
So each individual box has an agent on it that is provided by Datadog that happens to collect system statistics. So we're not using the virtual machine's onboard instrumentation for that. We do have alerts that fire per individual node. But because we're running in Amazon EC2, we're relatively unconcerned about an individual node and more concerned about a group of them. So we tend to be concerned more about an autoscale group's health rather than an individual node's health, because we'll just kill it and have it come back online. But we try to kill it after we've gotten enough information to understand why it went dodgy, because we don't want to have to be killing them hundreds of times a day. Ideally, we would never kill them. Did I address your question? Yep. Cool. Yes?
Great talk, Ryan. So you mentioned that you have a particular threshold before you're actually throttled with your timelines, right?
That is the case.
How close to that line do you walk in day-to-day operations?
As far away as possible. So the question was, we have an implicit throttling limit, which each of the exchanges, how close do we walk to that limit before we decide to make a federal case of it? And the answer is, as far away as possible, we stay from it. So about 2% gives us 3% of headroom, and we had seen that particular pattern for quite a while, and it was considered to be a stable divergence of the system. So we were able to live with it. But if we ever deploy and we notice that our timeouts have spiked up, or we're not Brownian walking around 0, then we make a case of it, because that is a new behavior that's been introduced into the system that is divergent from its goals. Yes?
How long is your data retention to analyze trends and that kind of stuff?
Yeah, so it depends. We push data into a couple of different places. In where it goes into HBase, we have never deleted anything since the company started. For Datadog, I believe their retention rate is 3 months. Maybe it's longer than that, but it's quite a while. And if we actually care about anything long term, we will push it through the HBase side of the house where we never delete anything. Questions?
The CPU shield,
Yeah.
elaborate on?
So,
I've never heard of that. I was just curious what that.
So the question was to elaborate on a CPU shield. Linux has the capability of dedicating certain CPUs in a box to the system and application-specific things. So you can actually cut up the number of CPUs into different groups and say that certain processes will run in a group. So common configuration is root, which contains all CPUs, system, which contains the background processes on the box, and then application, which is the way we're deployed. But I know I have seen situations where people will have 32 cores in a box, and they'll have 2 cores for background, 2 cores for moderately important background, and then the remainder for the primary application.
And then you just give up those cores for the background stuff. I mean, if nothing is needed, then they're just sort of idling.
Yeah, exactly. Yeah, and on a production system, you know, your background shouldn't be that hefty, right? Your box should be primarily dedicated to the system that you're working on, and we can't always make that, so shield them.
Okay, cool. Thank you.
Yeah. No more questions?